Welcome. Today, we are presenting our manufacturing plan for a peristaltic pump using mild steel provided by our College Mechanical Engineering department. We show you how we take raw stock and transforms it into a high precision assembly. To execute this project efficiently and maximize our limited shop time, our 4-member team was strategically divided into 2 specialized pairs, each tackling a specific manufacturing environment based on the part geometry. The first group took charge of the milling workshop. The workflow began with stock preparation using the horizontal bandsaw to cut the mild steel plate provided by the department down to workable sizes. From there, they moved to the milling machine to square up the stock, followed by precise drilling and internal threading operation to create the pump housing. Meanwhile, the second group was deployed to the turning workshop. They focused exclusively on lead operation because the specific mild steel component had a much larger diameter and required substantial material removal. The lead was the ideal choice. They handled heavy external turning, face cutting and critical internal boring to achieve the tight tolerance needed for the pump rotating components. However, before a single power switch was flipped or a single piece of mild steel was cut, safety was established as our absolute non-negotiable top priority. Operating heavy machinery like lathe machines, milling machines and drill presses come with inherent risks, which we mitigated through strict PPE compliance. Let's look at our safety protocol starting from the ground up. First, a properly fit workshop jacket must be worn and completely buttoned up. Loose clothing, unbuttoned sleeve, or dangling threads are massive hazards around rotating splinters and cutters. The jacket keep everything contained. Second, heavy-duty safety boots are mandatory. The workshop floor can be a dangerous place, littered with sharp metal swath from the mild steel, and our boots protect us from dropped tools or heavy raw materials. And finally, safety goggles must be worn at all times. Whether you are turning on the lathe or drilling a hole, high-speed razor-sharp steel chips are constantly flying off the workpiece. Protecting our eyes is paramount to ensuring everyone finishes the day safely. With our team organized, our material prepared by the department, and our safety protocols strictly enforced, we were ready to begin fabrication. Here is how the manufacturing process unfolded.
Next, we continue to the machining process. The machining process consists of two main operations, which is turning using a lathe machine and milling. Also, we use manual cutting. Each process has a specific purpose to produce the final component according to the engineering drawing while maintaining safety and accuracy. The first process is the lathe machining process. The purpose of this process is to reduce the outer diameter, perform a boring operation, and cut a cylindrical workpiece to the required dimension. First, the cylindrical workpiece is securely mounted in the lathe chuck and aligned properly. The suitable tool, spindle speed, and fit rate are selected. The machining begins by reducing the outer diameter of the workpiece until it reaches the specific size. After reducing the outer diameter, a boring operation is carried out. Boring is a machining process used to enlarge and finish an existing hole to achieve the required diameter, accuracy, and surface finish. Unlike drilling, which create a new hole, boring remove a small amount of material from the inside of pre-drilled hole using a single point boring tools. The workpiece is securely clamped to the leg chunk and the boring tool is carefully aligned with the center of the hole before machining begins. During the boring process, the spindle rotates while the boring tool is fed slowly into the workpiece. removing material gradually until the required internal diameter is achieved. The hole is measured regularly using vernier caliper to ensure it meets the specified dimension and tolerance. A properly performed boring operation produce a smooth internal surface, improve hole accuracy and consistency, and ensure the component fits correctly during assembly. The second process is milling. Before starting a milling process, the dimension of the workpiece are measured according to the engineering drawing to ensure accuracy. A vernier caliper is used to verify the initial dimension before machining begins. After confirming the measurement, the workpiece is securely clamped in the machine vise on the milling table to prevent movement during machining. Appropriate milling cutter is then installed, and then spindle speed and feed rate are set. The purpose of the milling process is to thin down the workpiece by removing material until the required thickness is achieved. The milling cutter gradually removes material from the surface while maintaining a smooth and flat finish. After the milling process is complete, any burrs are removed and the workpiece is cleaned before proceeding to the final manual cutting process. The final process was manual cutting using a hacksaw. At first, the workpiece was supposed to be cut using a lathe machine with a parting operation. However, due to the technical problems, the lathe could not complete the cutting efficiently and would have taken more machining time. Therefore, the cutting was done manually. Before cutting, the workpiece was measured and marked according to the engineering drawing. A small machining allowance was left instead of cutting to the final size. This allowed the finishing process to improve dimensional accuracy, achieve a smoother surface finish, and remove burr before the final inspection.
After the milling process was completed, the next step was drilling. The purpose of drilling is to create accurate holes for assembling the different parts of the peristaltic pump. First, the mild steel workpiece was securely clamped onto the drilling machine table to prevent movement during machining. The hole positions were marked according to the engineering drawing, and a center punch was used to ensure the drill bit started at the correct location. The appropriate drill bit was then selected, and the holes were drilled carefully to the required depth. Cutting fluid was applied during drilling to reduce heat, improve the quality of the holes, and extend the life of the drill bit. After all the required holes were drilled, the next process was tapping. The purpose of tapping is to produce internal threads inside the drill holes so that screws or bolts can be securely fastened during assembly. A tab of the correct size was selected based on the bolt specification. The tab was inserted into each drill hole and turned slowly while applying light pressure. After every 1 or 2 turns, the tab was rotated slightly backwards to break the metal chips and prevent damage to the threads. This process continued until the required thread depth was achieved. The final machining process was surface finishing using a grinder. The purpose of this process was to improve the appearance of the fabricated parts and remove any sharp edges, burrs, or rough surface left after cutting and machining. The grinder was carefully moved along the edges and surfaces of the mild steel components to smooth them and remove any imperfections. This finishing process also prepared the components for final assembly by providing a smoother and neater surface. Through the drilling, tapping, and grinding process, all of the fabricated mild steel components were completed with the required accuracy and quality. The drilling process ensured that every hole was produced at the correct position and size, allowing the components to be assembled according to the engineering drawing. The tapping process creates strong and precise internal threads, enabling screws and bolts to be securely fastened without damaging the material. This provided a reliable connection between the different parts of the peristaltic pump and helped maintain its structural stability during operation. Overall, this machining process played a significant role in producing high-quality components that met the required dimensions and functional requirements. By following each manufacturing step carefully, we were able to fabricate parts that were accurate, durable, and ready for final assembly. This ensured that the completed peristaltic pump could operate smoothly, safely, and efficiently while demonstrating good machining practice and proper manufacturing techniques.
Next, I will explain the 5 problems faced by our group, followed by the assembly, testing, improvements, and conclusions. The first problem was the cutting process. The original method required the lathe machine, but our group used the bandsaw for the initial cutting. The bandsaw was faster and suitable for cutting the raw material to the required length. The second problem was the inner dimensions of part 1. We followed the dimension in the drawing, but the silicon tube could not fit properly. Therefore, we enlarged the inner diameter slightly until the tube could fit inside the housing. The third problem was the availability of the lathe machine. All the lathe machines were being used by other students. To avoid wasting time, we used the milling machine to remove the unnecessary material. The fourth problem was the bearing housing. It was accidentally machined slightly larger than the bearing, causing the bearing to become loose. The original drawing did not require a screw to hold the bearing. To solve this problem, we used the 2 existing tab holes and added a screw. The screw head acts as retainer and prevented the bearing from coming out. The fifth problem was the contact between part 1 and part 2. The original drawing did not include a spacer, so both parts touch each other and could not rotate smoothly. We added a notch between the parts to act as a spacer. This created a small gap and improved the rotation. After completing the parts, we assembled the bearings, screw, washer, nuts, and silicon tube. We then rotated the mechanism manually to check the movement. After adjusting the screw and adding the spacer, the mechanism rotated more smoothly and the bearing remained secure. For improvement, the inner dimension should be updated based on the actual tube size. The bearing housing should also be machined more accurately. A proper washer or spacer should be included in the design, and machine usage should be planned earlier. In conclusion, our group successfully completed the peristaltic pump. Although we faced several problems, we solved them by changing the machining method and modifying the design. This project improved our teamwork, machining skills, and problem-solving ability. Thank you.